did when my sister went to do a Zuri's tonight, so she didn't want it. Oh, yeah. I tried.
I know, and we don't even have to do gravimetric analysis. She said, no, she was like, yeah, let's do gravimetric analysis, it's a really old school thing.
Oh, so you guys get a constant math.
So we don't have to do constant math.
The only reason I got my PhD was I had a compound that we couldn't get elemental analysis on for metals, iron and manganese, because it was air sensitive. So when we ran it through the AA, the results were inconsistent. So taking a procedure, probably circa 1930s, 1940s, I took my compound, dissolved it in nitric acid, sulfuric acid, hydrochloric acid in a crucible, heated it up, and then gravimetrically separated out the iron and the manganese, measuring them out. I even used the ashless filter paper. I found some of it that was in one of the other professor's labs. I actually cut it to size. And so yeah, knowing how to do gravimetric analysis is actually very important when you need it. It's not important if you don't, but like I said, in my case, I had a choice of if we ever want to publish this thing, and I want to get my PhD, well then I better get that elemental analysis. And the only way to do it at the time was gravimetrically. Yeah, good times. I actually cracked the fume hood. It was really funny. So you pull out the safety sash. Well, the thing is, I had this massive Fisher burner going to boil off the hydrochloric acid, sulfuric acid, nitric acid mixture, and I got it so hot that the temperature caused the glass to crack on the fume hood. You're not supposed to cook stuff like that in the fume hood, but yeah. So yeah, gravimetric analysis is still a very important technique. And they figured this stuff out almost 100 years ago.
Imagine 100 years ago.
And I'm not even joking, like I said, the books I was pulling the procedures from were from late 1930s, early 1940s. And the reason why is in X-ray crystallography, iron and manganese are right next to each other. So distinguishing, so we had a compound that had 2 irons and 2 manganeses in it. However, if you didn't have elemental analysis, you could make the argument maybe it's got 4 irons in it, or maybe it's got 4 manganeses and so forth. So I did the elemental analysis of, like I said, precipitating out the metals. Yeah, so good times.
Yeah, where's the closest bathroom be here?
I think right around down the corner. Okay, so to get us into new aspects of chemical bonding, again, it's important to take a step backwards and think about the fundamentals of quantum mechanics. The Bohr hydrogen atom, in that model, Bohr did calculations based on, and compared to experimental data, and showed you could model the electron as orbiting the nucleus, the way the moon orbits the Earth, or the Earth orbiting the sun, and that mathematically worked out just fine. And it's closer to center, again, this would be the nucleus. Fundamentally, this is perfectly fine. However, the Bohr model fails when you have 2 electrons or more. So if you try and apply the same model from hydrogen to helium, it starts to deviate significantly. And you have 3 electrons, and then it's completely wrong. And well, that doesn't seem like a very good model, considering how many elements we have on the periodic table besides hydrogen. Fundamentally, Bohr was treating the electron as a particle moving around the nucleus. Well, with Schrodinger's wave equation, well, obviously he's treating the electron as a wave. And again, where I left off is this is one of the most fundamental aspects of wave behavior. If we have a wave propagating through space. Now, a couple things before I put the second one in here. The scale next to it, 0, +1, -1, etc., that's a measure of amplitude, right? If we were talking about sound waves, what is amplitude measuring?
The distance between the trough and the...
Well, no, if we're talking about just like a sound wave. Amplitude.
Volume.
Yes, volume. In other words, how loud it is. If we're talking about light, it's how bright it is, and so forth. Now, as we are moving along this axis, our wave goes to 0. What's that called? Anyone who's not a physics person can answer that question. I'm excluding them. No, that you're thinking like a titration curve.
Is it equal?
It's a node, right? Node. 0 amplitude, right? Now, waves do this. This is something physics figured out for waves all the time. If a particle is moving through space, its amplitude going from plus to 0 to minus would look a little bit bizarre. But this is, again, what we're going to have to reconcile with quantum mechanics of this wave behavior. Now, if we have a second wave, same scale, I'm trying to draw them identical there. This one's a little bit bigger, but get the idea. We would say that these 2 waves are in phase. Their crest's going up, the trough's going down. And one thing I should mention, when the wave is going in the positive, jeez, kill myself. All right, I'll be a victim of the board. When the wave is going up, we say it has positive amplitude. And when it's going down, negative amplitude, or plus or minus. This is not the same as positive and negative charge. Okay? Positive and negative charge are again a different phenomenon. Now, again, with electromagnetic radiation, I'm sure you could, on physics, you could bring those 2 closer together. For us, we're just going to think in terms of going up and going down. This amplitude going up and down, we refer to it as phase. Okay, so we would say that the wave has positive phase, positive going up, or negative going down. And this, again, these these concepts with a two-dimensional wave are going to carry over to eventually our three-dimensional wave. If we add these two waves together, put my scale back, our wave is now going to double in amplitude. So we've added them in phase. We have what's called constructive interference. Now, on the flip side, I'll squeeze it down here. If we have the same wave, but now we add it to a wave that is out of phase. So we're my drawing's bad, but assume that the magnitudes are the same. Now the waves cancel, and this would be deconstructive interference. For audio, for designing a studio or a concert hall where they have multiple speakers, they have to be very careful, because if you don't have the speakers orientated in the correct positions, what can happen is you can get deconstructive interference or out of sync interference, and what will happen is some parts of the auditorium will be dead spaces. Other places, the sound could be garbled. When I was at a commencement at another school, they had the speakers pointing towards the audience, the students and the family, and we as faculty were just a few feet behind it. And what was happening was the sound waves, when they were getting to us, were just all out of phase, so everything was garbled. So even though there was a lot of noise coming from the speakers, it was out of phase, and we couldn't make any heads or tails of it. Now, we're going to see that this concept of our two-dimensional wave is eventually going to come back to us for our atomic orbitals. And again, this is one of the things that I see all the time, even with upperclassmen, where they forget the fundamentals that the atomic orbitals that we're going to start defining right now are described as waves or wave functions. And everything that we've just talked about as far as amplitude and phase and nodes and so forth, all of that applies to our atomic orbitals, to our waves. But many times when people are describing an atomic orbital and they see that it has a positive phase, they think that means positive charge, which is not the same thing. So again, you have to be very careful of charge versus phase. So again, this brings us to Schrodinger and the wave equation. The Bohr model, again, failed. So with Schrodinger, and this would have been in the 1930 time frame, he's describing the electron's behavior purely as a wave. And this is actually analogous to how the intensity of light is measured. Because if you think about it, if you have a region of space and you want to know what its relative illumination is, well, how do you do that? Well, again, physicists figured this out a long time ago. So he applied it to the electrons. Now, we're not going to look at the Schrodinger wave equation itself, okay? If you think of, a parabola, y equals x squared, right? It's an algebraic formula. You can graph it, right, and get yourself a parabola. That's basically what Schrodinger's wave equation is doing. What we're going to look at are the variables, the quantum numbers, because chemically, those are going to be the most relevant to us. Now, I say most relevant. I'm sure Professor Fuhrer, who teaches PChem 2, where they derive everything from Schrodinger's wave equation, would basically say, well, we need to do the math. But what we're going to do is we're going to skip the real math and jump right into the result. So the variables for Schrodinger's wave equation, so the first one is the principal quantum number. And this is symbolized lowercase n. I'm skipping all of the experiments that got to this point. So for example, the ultraviolet catastrophe, photoelectric effect, de Broglie, etc. If, again, your 111 is a little rusty, read through the, not just our textbook, but the general chemistry textbook, that OpenStack book that I gave a reference to. And that will give you some of the historical context, because again, I'm not going to spend 2 months on that. N is defining the energy of the atomic orbital that we're describing and its relative size. Higher energy means that it's bigger. The allowed values for n are 1, 2, 3, all the way to infinity, but they must be integers. They must be whole numbers. And again, this comes back down to the most fundamental aspect of quantum mechanics. Off to the side, if I have classical mechanics, all values of energy are allowed. In quantum, okay, so this would be classical. In quantum mechanics, we have energy levels. 1, 2, 3, 4. Planck first worked this out, and the value he used for the energy steps was n. So Schrodinger is basically using the same thing. We're going to find that physicists typically, if they have a theory and it doesn't quite work, often if it's got some terminology in it that's useful, that terminology or variables will kind of get carried over. So for example, the orbital concept or the orbit that Niels Bohr defined, we're going to call them orbitals going forward. So again, it's one of these things where we're using the terminology, but it's not actually exactly on point of what it should be. N equals 1, 2, 3, all the way to infinity. Do we need to go to infinity if we're in a chemistry class?
No.
What does N represent on the periodic table? N equals 1, 2, 3, 4, 5, 6, 7, right? It's the row number, okay? Quantum numbers are going to give us the periodic table. Who gave us the periodic table that we use today in the first place? About what, when?
1970.
So what are we, 1400s, 1500s, where are we in time?
19th century.
About 1870-ish, yeah. Now the thing is, Schrodinger, he did his work around the late 1920s, 1930s. So Mendeleev figured out the periodic table like 70 years before quantum mechanics was sorted out, to do this. Mathematically, the Schrodinger wave equation generates the periodic table. Okay? So a perfect example of this is when Mendeleev made his periodic table, he didn't have a group 18 because nobody had discovered the noble gases. Why would he add another column on there when there were literally no elements that had been discovered? Well, we'll see. Obviously, when we go through the quantum numbers, it's going to account for all of the elements going forward. So that's one of the the absolute strengths of Schrodinger's wave equation, not just its behavior of the electron, but the fact that it's used to actually generate the periodic table on a mathematical basis. So this defines, again, the size and relative energy of our atomic orbitals. Our next quantum number is angular momentum. That's going to define the shape of those atomic orbitals. And this is L. Your book puts the word orbital into it. Some textbooks just call it angular momentum, and it's fine. I'm going to talk about shape very briefly today. This will be something that we will come back and keep revisiting over and over again. In this course, already you should know the s and p orbitals, right? You will need to know the d orbitals as well, but that'll be something we're going to be looking at a little bit later on. L, here, is 0 through n minus 1. So this is why n is the principal quantum number, because we're going to see that the other quantum numbers are relative to it. For our values of L, first, the orbital designation. So if we have L equals 0, okay, this is our s orbital. L equals 1, P, 1, 2, D, 3, F, 4 would be, at this point after F, it just becomes alphabetical, and then it becomes G, and so forth. But with all that buildup, the important thing is, ignoring helium, groups 1 and 2, S. 13 through 18, ignoring helium, P. Then 3 through 12 are the D, and then we have the F block with the lanthanides and actinides. So the way you should be thinking about the periodic table is based on the atomic orbitals that are filling. So again, S block, P block, D block, and F block. Now, again, one of the things we'll talk about a little later, why is helium in group 18?
Full valence.
Well, neon is a gas,
Because it acts more.
argon is a gas, right? Krypton is a gas, helium is a gas, right? But from an electronic point of view, helium actually belongs over here. But because beryllium is a solid and everything else is a relative high melting solid, it's chemically moved over here. So we're going to see that the periodic table, which we kind of hold in this holy regard, you can actually say, well, wait a minute, this is wrong. You have to decide which way do you want to organize it. Do you want to organize it based on physical properties, or do you want to organize it based on electronic properties? So again, electronically, we're going to see helium is actually S block. It should be over here. Or you can make the other argument, and I've seen this on periodic tables, where hydrogen should actually be over fluorine. You can make that argument as well. And they're both valid, because think about it, hydrogen's a gas at room temperature, 1 atmosphere, whereas lithium and everything below it is a metal, a solid. Yes?
This might be kind of a dumb question, but why is helium electronically, should it be in group 2?
And we're going to talk about that because of the electron configuration. So,
Oh, okay.
yeah, and we're getting, in other words, and we'll go through ground state electron configurations once we finish the quantum numbers, but if you recall, 1s1, 1s2, right? That's the electron configuration for hydrogen and helium. So we don't have any p electrons for helium, hence it should be over there. But because it's a gas, it's over here. So again, this is where starting to kind of look at the periodic table in a little more critical way of saying, well, wait a minute, why are these elements? But again, going back to L, We have our S block of elements, our D block, our P block, and F block. For Gen Chem and organic, or a little bit of over here for organic, and pretty much everything like right around here. Organic chemistry doesn't like to, to go out very far, so they'll have carbon, nitrogen, oxygen, the halogens. Little sulfur if you want to get into thiols, and then a little bit of phosphorus, but that's it. So, organic chemistry is kind of the discount. Whereas inorganic chemistry, we're very inclusive. We include all the elements, even ones that don't exist. So, why is it SPDF instead of like alpha, beta, gamma, or something more rational?
Because that would be too easy.
Exactly. And again, this is another thing we can blame on physicists. Oh, yes?
Doesn't it correlate to the actual shape itself?
No, it's actually predates shape. So what you have to remember in this time frame, going 1890s and beyond, people were still doing experimentation. Spectroscopy. You could burn stuff and you could see colors. You could if you had like fancy setups, you could get the different wavelengths of light. And as different signatures for the elements were being observed, they were given basically names for those particular things. So in the case of, for S, it's spherical. At the time, I believe it was actually more a reference to the symmetry rather than the orbital hadn't been defined. But for P, it's principal. And the reason why is the spectroscopic signature that correlates to what we now call a p orbital was a very well-defined peak. In other words, it was the principal peak. So there were other peaks, and then there were these more dominant peaks. But it depends on the element, because if you were looking at calcium versus selenium, you'd have a different set of lines, right? Spectroscopic lines. So these terms are coming from spectroscopy. D is diffuse. Well, what do you think the spectrum of the transition metals look like, right? They're diffuse. The d orbitals tend to be a little bit broader, and how they can interact with other molecules like water tends to take their spectrum, and instead of having a nice sharp line like you see like in your classic analytical chemistry books where it's like this no volume of perfect, the lines broaden out, they're diffuse. And in the case of the lanthanides, it's fundamental. And the reason why fundamental, if I have a lanthanide europium, and I have it in water, and I look at its spectrum, I'll see a signature. If I add ammonia or some other ligand to it, let's say I change from chlorine to bromine to fluorine or whatever, the spectrum stays essentially the same. So it's fundamental, it's not changing. And we understand chemically why that's happening right now. But again, in the very early days of quantum mechanics, there was lots of data, but no explanation. So the fact that the spectrum was not changing, that's where the term fundamental came from. And again, I'm sure a lot of these terms were just basically graduate students late at night at a pub, trying to look at their spectra, look at their data, and figure something out. And afterwards, we go alphabetical to G and so forth. We run out of elements on the periodic table, so we don't have to worry about G orbitals and anything else like that. Uranium is the last natural element, and then everything else is man-made, synthetic. And then we have these pseudo things from the super colliders and all those things that last like a femtosecond and so forth. But so S, P, D, and F, just to know that, again, those terms, they're obviously integral to what we do, but there's nothing special about why it's S, P, D, and F. In other words, it was literally just somebody saying, if they would have called the spectrum wide instead of diffuse, then it would be W, right? In other words, so again, just to have a little bit of context. We will come back and look at the actual shapes and phases of each of the atomic orbitals, but right now I'm gonna gloss over that. So we have L, our angular momentum. If we take our atomic orbital and place them, or atomic orbitals, and place them in a magnetic field, what we find is that the orbitals will actually change orientation when they're in a magnetic field. So the next quantum number is the magnetic quantum number. And this is M sub L. This defines the relative orientation of the orbital to the nucleus.
Only when there's a magnetic field present?
Yes, and that's how you resolve them. Even when there's, in other words, it gets, you can have, in other words, so let's say I have 3 orbitals. If there's no magnetic field, they're essentially degenerate. They're at the same energy. When you put a magnetic field, then you can actually see them separate. And that's done with spectroscopy. If any of you have had organic with the NMR, for example, you place an organic sample into a very powerful magnetic field, but then you have to actually hit it with radiation, hit it with RF, and then you can start seeing signals from it. So
that ML is like a measurement that's already defined, that's never...
no, and I'll show you the term for ML. So it's going to define the orientation relative to the nucleus. In XYZ coordinate system. For those of you who get to take PChem 2, you get to use polar coordinates. So good times, good times. But for us, we're going to stick with X, Y, and Z. The way we define M sub L, it's negative L through 0 to positive L. Now, and again, going back to your question, well, what does that mean? Well, if we look at an s orbital, an s orbital has L equal to 0. Okay? So there's one atomic orbital s per end shell. But it's 0, so L is 0, so M sub L is 0. Okay? That doesn't mean there's no orbit or no orbital. What it's telling you is there's one orientation. And, well, what has one orientation? A sphere, right? A sphere, regardless of where you look at it from, it's a sphere, right? So when L is 0, M sub L is 0. And that's how we get our sphere for the s orbital. Because no orientation is going to be different. But now when we go to our p orbitals, when we go and we have L equals 1, M sub L can have 3 values. -1, 0, +1. And that's where we get px, py, pz, right? We have 3 orbitals, and they can be orientated on the x, y, and z axis, right? Basically a Cartesian coordinate system. Right? Now, again, before I don't lose anybody, we're going to see, spoiler alert, you can have 2 electrons in an orbital. S, we have groups 1 and 2. We have 3 p orbitals. That gives me 1, 2, 3, 4, 5, 6, right? So we're going to see that this M sub L is actually showing us the rest of the periodic table. We're filling it in as we go along. Okay? What happens when I go to L equals 2, the d orbitals? What are my allowed values? Exactly. -2, -1, 0, +1, +2. Now we have 5 orbitals. S, there's just one orientation, a sphere. Easy enough. We'll see, obviously with the P, we have the lobes, and I'm not going to draw them right now. We're gonna come back to that. And then with the D, now you got 5. Now with the E, it gets more complicated because of their relative orientation. You have 3 that are diagonal to X, Y, and Z, and then 2 that are actually on X, Y, and Z. But we'll come back to that. Later in this course, we will go into transition metal chemistry in a very rigorous way, and the only way to understand it is to know the d orbitals. Okay? In your organic chemistry classes and in Gen Chem, you can get away with just knowing S, PX, PY, PZ. Okay? How many of you are in organic right now or have taken it? All right, okay, good, good. So you'll learn, you know, if you haven't, of like orbital hybridization, like with the p orbitals. If you want to make a double bond, you need to have orbitals that are lined up. You know, in the case of, you can have, you know, a sigma bond, and then you can have, you know, pi bonds and so forth. We're going to see all of that happens in much crazier geometries for the d orbitals and so forth. And I won't run out of space, but F, by the way, so 1, 2, 3, 4, 5, right? And well, we have 10 for our d orbitals, right? So 5 orbitals, 2 electrons each, and so forth. And then we get to L equals 3, F, and now we have the 14 elements, right, for that. N, L, and M sub L define the atomic orbital. And again, this term orbital is carried over from Niels Bohr using the term orbit. If Niels Bohr hadn't used the term orbit, you know, I'm sure Schrödinger would have referred to this in some type of wave mechanic or something boring like that. Now, we've got our atomic orbital, and that's what Schrödinger's equation gives us. What about the electron? Okay? I'll start with helium. So let's say we have an ion source, and it's generating helium atoms. So each one of these is a helium atom, and it's neutral. It's not helium 2 plus or anything, you know, it's not like an alpha particle. And just for fun, I shoot it through a magnetic field. So what's observed is the helium atoms just go right through undeflected. But if we do the exact same experiment, but now with hydrogen atoms, okay, and again, these would be hydrogen neutral, not hydrogen, not H plus. Okay, so these are neutral hydrogen atoms. We get a very different result. They split 50-50. Half are attracted to the North Pole, half are repelled by it, and vice versa with the South Pole. What's going on? Well, hydrogen has 1 proton and 1 electron, so it's going to have the electron configuration of 1s1, right? And I'll go, you know, give you a refresher on generating the ground state orbitals. 1 electron, so, well, the s orbital can hold 1 electron. Helium has 2 electrons, okay? And that gives us what we now know as 1s2. If we look at this graphically, the electron has a negative charge, okay? If we have 2 of them for helium, it goes through this magnetic field undeflected. But if we only have 1 electron, it's repulsed. And what's going on? Well, this is actually a known phenomenon. If you have a charged particle and you spin it, it generates its own magnetic field. So what was realized is that the electron itself can have 2 states. It can have what we call a spin-up magnetic field, and you can think of this as the electron being a north pole, And you can think of this as the electron being a south pole. So this is electronic spin, or m sub s. So the electron has a magnetic property. The values for m sub s are positive 1/2 or negative 1/2. And again, this is to make it more mathematical, but again, what you can think of is, you can say the electron is behaving as a north pole or a south pole. Now, if we look in the case of hydrogen, I have two possibilities. The electron can be what we call spin up, or again, you can call it positive 1/2 or a north pole, or it can be spin down. Statistically, it's 50-50 because there's no difference in energy of a north pole versus a south pole, right? They're equivalent. But what about helium? Why is it going through this magnetic field without any issues?
They have a one up and a one down.
Exactly. Now we have two electrons. The first one goes into the orbital, spin up or spin down, doesn't matter. And then the other one has to couple with it. We can't have two electrons in the same orbital with the same spin because it would basically be taking two north poles and trying to put them together, or two south poles. So the electrons couple together. This is one of the paradoxes that was kind of resolved in physics, because the idea of taking a bunch of charged particles, electrons, and then shoving them all together, well, they all have negative charge. Negative charge repels, right? If I have a negative and a negative, they repel. But this magical quantum mechanical feature of spin gives a way for the electrons to couple together. All right? So, two electrons per atomic orbital, and they go in with opposite spin. And again, that's what this experiment is showing, that helium, the electrons are coupled together, and we refer to that as diamagnetic. So all the electrons are paired together. But in hydrogen, you only have one electron. Obviously, it can't couple together. And this is known as paramagnetic. Diamagnetic is actually slightly repelled from a magnetic field. In this case, because of symmetry, you wouldn't actually be able to notice that. So diamagnetic is slightly repelled by a magnetic field. Paramagnetic is strongly attracted to a magnetic field.
So it's not attracted or repulsed, it's just attracted?
Yes, if it's paramagnetic. Yes. And in this case, I'm using the term paramagnetic in a very broad sense. In other words, if you talk about specifically which pole, then you would have the repulsion. So you could actually say strongly attracted or repelled, but just to keep it simple. So I'm not going through every single case. What paramagnetic and diamagnetic, what does that fundamentally explain? Something that you've observed since you were children. Hopefully something that led you into science.
Magnetism.
Magnetism, magnets, yes. This, spoiler, yeah, this explains magnetism. Now, the thing is, for most magnets, they're here or down here. In other words, d electrons and f electrons. So what you find is certain materials like iron, cobalt, nickel, or some of the lanthanides are very, very good at producing magnets because they have a lot of unpaired electrons. Okay? Other compounds are diamagnetic. Most organic molecules are diamagnetic. So they're not gonna act as a magnet, you know, you're not gonna, and now the thing is, just because something is paramagnetic, magnetic, doesn't mean it's like something you can just stick onto the wall like a refrigerator magnet. There's actually more that goes into bulk magnetism. But this basically opens the door to it, of diamagnetic and paramagnetic, and then you have to like actually look at the bulk material. That's actually stuff that I cover more in Chemistry 416 than in this course. But in other words, they are related. In other words, if you have a material that is magnetic, it has to have some paramagnetic component within it that causes that. I'm not going to go through a ton of ground state electron configurations. I just want to go through a couple before getting into something else. Again, with hydrogen, we have one proton, therefore we must have one electron. Again, potassium, 19 protons, 19 electrons, when it's neutral, and so forth. What Schrodinger's quantum numbers are doing is, if I have 22 electrons, I need to generate enough orbitals to put those electrons into. That's why we see the periodic table get wider as we go down, because with each n level, we create more subshells, more L levels, and so forth. We don't always fill them in some cases. So hydrogen, our designation for ground state electron configuration. So N is, or 1 is our quantum number, N. And then we have 1s1, helium, 1s2. I'm gonna skip around. We will be doing, again, tons and tons and tons of ground state electron configurations. And again, this should be a refresher from 111. So how do I get to carbon? All right. Well, can I have 1s6? Right? No, you can't shove 6 electrons into one orbital. That's why you go to the next one. And again, the way to read the periodic table, and this is what I was talking about, why helium is in the wrong spot. Helium should be over here. 1s1, 1s2, right?
Full orbital.
2s1, 2s2, 2p1, 2p2, etc., right? So in other words, when you look at the periodic table, you should just count over, and you can literally read the electron configuration from it. And that's where remembering S block, P block, D block, F block. So we start at the bottom. What's that called? Whose principle? Off-bow, very good. Off-bow means building up principle. So we always start at 1s1 and then go from there. So whether we're talking about uranium or you know, vanadium or whatever, you always start at the bottom and build up. So we got our first 2 electrons, but now we need to go to n equals 2. When we get to n equals 2, we generate 2s and now 2p2. Again, boron would be 2p1, carbon would be 2p2. Is carbon diamagnetic or paramagnetic?
Paramagnetic.
It's got 2 in the p, but what we have to remember, 2px, 2py, 2pz, we place the electrons into separate orbitals before pairing them. Okay? This is Hund's rule. Why? Why not just pair these right now? What's the charge of an electron?
Negative.
What's the charge of another electron?
Negative.
Same charge, they repel. Electrons don't want to be next to each other if they can avoid it. In this case, they can avoid it, right? So you just go into another orbital, subshell orbital. When we get to P4, then we start to have to pair the electrons going forward. So again, this is something that hopefully is review. Now, I want to open the door to some of the new stuff. We will definitely be, again, going through electron configurations and many other things. How do we get to a molecule?
Very carefully.
With your Lewis dot structure, you can just say, oh, single bond, that's all fine and good. But to look at this in a more rigorous way, we have to think about, well, why is diatomic helium just not allowed? Right? And you can make arguments about closed subshells and blah, 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 but those are really not a true explanation. Well, we have to go back to the basics of when we're trying to go from an atom to a molecule, we put electrons into chemical bonds, but those chemical bonds are formed by combining atomic orbitals, right? So a better way to think about making hydrogen, so we have a hydrogen, and this would be its 1s orbital, and then we have another hydrogen, and that's its 1s orbital, and these are waves, or wave functions, right? So an s orbital, right? S orbital has positive phase. In this case, I'm just using black. I'll eventually use different colors. These, again, these are the atomic orbitals. Forget about the electrons. Just think in terms of orbitals at this point. If I have two waves and they have the same phase, how do they add? Constructively. Now, as it turns out, from an energy point of view, let me just put an energy thing here. If we add, so let's say these are the hydrogen atoms. If we add these two waves together constructively, we generate a new wave at lower energy, lower relative energy. Okay? And that's our chemical bond, and that's what that would be. But we're forgetting something. If I can add waves constructively, I can also add them deconstructively. When we add two wave functions together, we get the bonding version, the constructive interference, but what we also get is the deconstructive interaction. Okay? Again, this would be, kind of think of this as like the 0 point in energy. Now, this, so this is a bonding orbital, or a molecular orbital, and this is an anti-bonding molecular orbital, or MO. How many electrons does each hydrogen bring to the party? One. So I have two electrons, they go into the bonding orbital. The anti-bonding orbital is empty. So everybody's fine. This orbital is empty. I'm going to redraw this, and we'll be doing this quite a bit. I'm going to redraw this in a more schematic way. So this is sigma is bonding, sigma star is anti-bonding. So let's play the same game of combining these orbitals, but now let's do it with helium. How many electrons does each helium bring? Two. So I'm going to have 2 electrons here, 2 electrons there. The first 2 go into the bonding orbital. Well, where do the other 2 have to go? Anti-bonding. If I have a wave that's in phase and a wave that's out of phase, what do? They cancel each other out. So for diatomic helium, the bond order is 0. Because the waves literally cancel itself out. This is a case where having too many electrons prevents it from actually forming a chemical bond. Okay? What you've just dipped your toes into is called molecular orbital theory. So this is the monster under the bed that your parents told you didn't exist. This is how we can explain everything that was wrong with general chemistry, chemical bonding, and even organic chemical bonding. If you had organic, you know, the aromatic rings and all that donut stuff, that's actually the bottom half of the molecular orbital diagram. In Gen Chem, you learn this part of the MO diagram, not this part. And the reason we're going to need this is because in some cases, the antibonding MO is partially filled, and it will play a role in the chemistry of the molecule. Right? Now, before you run off, these are basically empty MO diagrams, just to kind of get you started. The top one is the S, and the bottom one is for the p orbital set, and we'll be going through that. Yes? I will send out an email about the alleged quiz, which is just a vague idea in my mind right now. It's growing stronger every moment.
Would it be the stuff we talked about?
Yes, it'll be quantum mechanics. So everything that I talk about in class is fair game.
Is this how we figure out whether something can or cannot bond?
Yes, yeah, in other words, and again, with the MO diagram, we're going to spend a lot of time going over this. So I want you to have it right now. And don't worry about, I'm gonna start over on Monday, or on Friday, of going back through MO diagrams. So I just wanted you to see it, and hopefully read through your textbook, get to MO diagrams in your textbook and start reading through it, because it is very fundamental of why hydrogen can form a single bond, but helium fundamentally cannot. And it's because wave in phase, wave out of phase. And it's so easy to forget that. So anyway, I will see you on Friday. And yes, I'll send out an email. All right. Yes. Yes. Okay.